Hey everybody, this is Larry. This is me going over Q4 of the Leetcode Daily Weekly Contest 207. Minimum cost to connect to a group of points. So this is a very tricky problem. Let's see how many people solved it. As of right now, about 114. Yeah, so I think the first thing to notice is that n is equal to 12 on both sides. So for me, I just did this with sort of brute force, but a tricky brute force with dynamic programming, memorization. And then you could probably convert it to bottoms up. And it took me a long time to get it, even though the code is really short, relatively. But I'm going to explain the states. So states is that basically for each, index is equal to the current processing index on the left side. Used is equal whether index was used on the left side, because you want to force it at least once. Index 2 for variable name is current processing index on the right side, and mask is equal to whether the bit mask of what was used on the right side, right? And so those are the states, and it took me a long time to come up with this. So sometimes when you watch other people do this video, like, it's gonna look like magic, right? But so you watch me solve this after the explanation, you can kind of see my thought process as I go on, hopefully. But and I did get a wrong answer submission. But the idea is that and there is a progression that I made during the contest, and I had some mistake, but this is the states, right? And the thing that I would think about is that, okay, index is equal to 12, or like the 12 possible index uses 2 times index 2 is 12 times mask, which is 2 to the 12 power, and then I plug this in a calculator. It seems fast enough, so that's how I was able to that's the kind of math that I would do during a contest to figure out whether it's worth or it's able to do it. And basically, given these inputs, the question is, what is the min cost of connecting two groups, given that my computer's lagging a little bit. Given that we used index -1 on the left side. Sorry, computer's slow, so I'm trying to see what's up. Index 1 on the used side, index being used or not. Index 2 on the index 2 in this case on the right side for the current index. And the bit mask of what has been used, right? So what I mean by this is, and give me a second, I'm gonna pull out the good old paintbrush. I'm trying to be a little bit more visual because people seems to like it. Should have had it. Yeah, so basically you have some nodes on the left side, and basically our idea, and the right side say, is that we want to process the left side one by one, right? So we're going to start drawing lines. Okay, let's say for the first one, the one on the left, we draw. Let me choose another color. We draw, this is good. Okay, good. We draw this is good. Okay, right? And then we this is a brute force, right? So then the index 2 in this case would indicate, for example, let's say we're on to here. And we don't keep states between different index 1s, but it's basically a for loop of, okay, for index 1, for the subproblem of one, each node on the left side, do we use a node on the right side, right? So that's kind of the question for this problem. And for example here, let's say you have some costs already, and we want to go, okay, so in this case, the bit mask would look, on the right side would be like, okay, we use the first node on the right side and the second node on the right side. So this is our state, and we're on to the third node. And now we will go through, is index 1 connected, index 1 connected to index 2? Do you want it to? And then we brute force that. Let's say yes in our current recursion, then we try the next one. Or not, we have different choices. But basically, this is a way to enumerate all possibilities. And that's kind of the way that I would think about it. Hopefully that was a little bit clearer, but we'll go through the code together given this definition of the problem. So given this definition of the problem, then if index is on the left side, that means that we've done everything on the left side, but we have to check if we've done everything on the right side. If we've done everything on the right side, that means that there's no additional cost, then it's 0. Otherwise, we return an infinite value because that means that the current configuration is not legit. We did not use everything on the right side of the list. And then we go through, if index 2, that means that we've used everything on the right side, then we check whether we used the current index, right? Because every index on the left side has to be used at least once. And if this is used, then that's good. We just go to the next index on the left side. We start over with it not being used. We start with the first index on the right side, and then we pass along the mask. However, if we don't use it, or we haven't used the left side node yet, then we convert this into infinity. Right, because that's not a valid configuration. And again, the default configuration would be infinity. I don't know why I need to just write infinity for this. But yeah, and the cost, of course, this is the cost of connecting the left and the right of the index left and index right. And if it's used, then we can also skip the rest of the index 2 as a possible path. It doesn't have to be a path, but it's a possible path. And I think technically speaking, this doesn't matter because eventually one of these two paths would go here. But I just wanted to put it in, I think. And this path is okay. Whether this is used or not, let's just skip. This is not using the current index on the right side. That means that given these two nodes, I don't want to use this one on the right side. And this path is okay. Given these two nodes, I do want to use this current node on the right side. So then what does that mean, right? Because this one is pretty straightforward. Just move the index by 1. But in this case, it means that, okay, use is true. That means that you used the index on the left side. So we want to switch that state. Index 2 plus 1 is still straightforward. And also the mask, which keeps track of stuff that you've used on the right side. Well, we flip that bit so that it shows that we used that bit on the right side. And then we add the cost because this is the cost of connecting index 1 and index 2 on the left and the right respectively. So that's kind of the algorithm. Once you're able to get, the hard part obviously is not, the coding. It's kind of phrasing this question and coming up with these states. It was pretty tricky for me. So definitely it's not, simple. So what is the complexity of this? I think I alluded to it earlier. So index is going to be O of n1, where n1 is the left and n2 is the right, times 2 times index 2, which is n2 times 2 to the n2, right? So this reduces to, n1 times n2 times 2 to the n2. So this is the number of possible states or possible inputs to possible input. And for each one, against you look at the complexity of the code, this is just O of 1 because we do O of 1 operations everywhere. So work per input is equal to O of 1. So the total time complexity would be O of n1 times n2 times 2 to the n2. And total space complexity is just you go to the number of, so it also takes one space per input. So it means the entire thing will be O of n1 times n2 times 2 to the n to the 2. 2 to the n2. I don't know if I said that right, but yeah. So that's the time space complexity. Cool. That's all I have. Oh, I didn't remove this, so you could see the code a little bit better. I hope I didn't block too much of it. Sorry about that. But yeah, take a look at this code and yeah, let me know what you think. Hit the like button, hit the subscribe button. Watch me solve it live next. See ya. Really slow day today. Okay. 7 people have finished. Seems like maximum bipartite matching. Except for that things are 12, so you can do min cost max for. Is there always a solution? I guess so, because it's a full graph. Oh, do you have to choose the point? Oh, no, that's not. Oh. Still min cost max for, but I don't have that coded. Okay. What do you need to do? More better something. Is it symmetric? Oh, I guess it's not symmetric because it doesn't make any sense. Is there any mods? Ooh, wrong answer on this one. Okay, because I have to go the other way. How do I clear the cache on this one? I actually don't know. Oh, but this assumes that one on the left is one on the right. But so 12 times. Is that too slow? Maybe. 200 million operations. Would have totally submitted some quiet if this case was here. Don't tell me it's max for. I have to take a my. That would have been funny. Does max for work? Maybe not, because it's not a bipartite. I mean, it's bipartite, but this is not maximum bipartite matching, because one edge can be on multiple. Question is, this is too slow though. If this is fast enough, I'm gonna be a little bit sad, to be honest. This went better than expected, I guess. Because it can be 0. But it's probably too slow. Even this is too slow, to be honest. Yeah. Yeah. It's fast enough, at least. Though it's wrong. This is actually weird. It's actually really weird. They say saying this happens all the time. Oh, maybe I just miscounted. Yeah, okay, so there's more of one than the other. That's okay. That's what I was expecting. But that means that it's even slower. Yeah, we want to run something that's 1,000 slower. Huh. Oh no, even if I do in order of 10 operations, it's too slow. Based off. Okay, actually. It's a little bit slow. But let's YOLO this. Like I was close to. Really depends on the number of test cases, which is why it's weird. Oh. And I don't need to do this. Maybe I just need to do, now that I think about it. That's not good. Now you need to the right answer? Nope. Oh. This is pretty slow. But why? It has a million states. Come on. Hey, yeah, so that was the end of me solving this problem during the contest. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord, ask me questions, let me know how you did, how you feel, and I will see you during the next problem. Bye-bye.